Hello friends, I welcome you in lecture number 34 on relations. In this lecture, we are going to discuss one question on equivalence classes which was asked in GTU Winter 2021 exam. In lecture number 33, we have understood what is equivalence class and we know how to decide equivalence classes of elements of given set corresponding to the given relation. So we are going to discuss this question in this lecture. Question is, define equivalence class generated by an element x in a set, say capital X, and let Z denote the set of integers and let R be the relation called congruence modulo 3 defined by R equal to ordered pair xy where x and y are integers and x minus y is divisible by 3. Determine the equivalence classes generated by the elements of Z. We have already seen this congruence relation. Here we have congruence modulo 3. Therefore, we are considering those ordered pairs xy of integers for which their difference is divisible by 3. And we know that this congruence relation is an equivalence relation. So we can talk about equivalence classes corresponding to this congruence relation. First part is to define equivalence class generated by an element x belongs to x, and we have already seen the definition of equivalence class, but we are again writing here for revision. So suppose we have some relation defined on a set, say capital X, let R be n, and that relation must be an equivalence relation. Let capital R be an equivalence relation on a set, say capital X. Then for element small x in capital X, the set we are considering those elements of given set X such that those elements are relatives of X, that is y belongs to X such that X is related to y. So this set is called an equivalence class generated by this element, generated by an element small x which is a member of given set capital X. This is the first part of the question. Define equivalence class generated by an element x belongs to capital X. Now in this part we are considering capital X equal to set of integers, and we have taken this congruence relation on the set of integers, and we know that congruence relation is an equivalence relation. Therefore we can talk about the equivalence classes generated by the elements of Z with respect to this congruence relation. So first we are writing that congruence relation here. We are given that R is the set of all those ordered pairs x comma y such that I am writing in this way: x and y are integers and x minus y is divisible by 3, and we can decide the equivalence classes corresponding to this R. We know that R is a congruence relation and it is an equivalence relation. We know that congruence relation is an equivalence relation. Congruence relation R is an equivalence relation. Equivalence relation on this set of integers that we have shown in earlier lectures. Now we have to decide the equivalence classes generated by the elements of set of integers. Now we know that in this set of integers we have infinite number of elements. We are having positive integers as well as negative integers and 0. Here I have infinite number of positive integers. Here also on this side I have infinite number of negative integers. So we have to decide the equivalence classes generated by all these integers. Now if you recall, in earlier lecture we have discussed that if two elements, say x and y, are related to each other, then equivalence classes generated by x and y will be same, and x is always a member of equivalence class generated by x. And we also know that if we consider any two equivalence classes, then either they are equal or disjoint, their intersection is empty set. So using this property, first we can find out equivalence class for certain integers, and then using this property we can write down the equivalence classes corresponding to other integers, or we will see that we will have finite number of distinct equivalence classes. Majority of equivalence classes will be same, because for example, if I consider 6 and say 9, then 6 9 is member of R, because 6 minus 9, that is minus 3, is divisible by 3. So equivalence class generated by 6 and 9 will be same. Similarly, 6 is related to 3, because equivalence class generated by 3 and 6 6 is related to 3, because 6 minus 3 equal to 3, which is divisible by 3. Therefore equivalence classes generated by 6 and 3 are also equal. So we can see that if I consider multiples of 3, then equivalence classes generated by 3 will generated by all the multiples of 3 will be same. So in this way we can have disjoint equivalence class. We have distinct equivalence classes finite in number. There are infinite number of elements in this set of integers, but equivalence classes generated by all those infinite number of integers are going to be same, that we will see. And for that we are using this property, that if two elements are related to each other, then equivalence classes generated by them are always equal, and if two elements are not related to each other, then equivalence classes generated by those two elements are disjoint, that is, they will have no element in common. For example, if I consider 0 and 1, then I know that 0 minus 1 is not divisible by 3. Therefore 0 equivalence class generated by 0 and equivalence class generated by 1 will be different. Similarly, equivalence class generated by 2 and 1 will also be totally different. Their intersection will be empty set, because 1 is not related to 2, because difference of 1 and 2 is not divisible by 3. Now you can see, if I consider equivalence class generated by 0 and say equivalence class generated by 3, then these two are going to be same, because 0 is related to 3. 0 minus 3, that is minus 3, is divisible by 3. Therefore 0 and 3 are related. Therefore equivalence classes of 0 and 3 are same. Same thing for all these multiples of 3. So all these equivalence classes are going to be same. Similarly, we can see that if I consider ordered pair 1 and 4, if I consider ordered pair 1 comma 4, then this is an element of given relation, because 1 minus 4 is nothing but minus 3, and this is divisible by 3. We can write minus 3 as minus 1 into 3. Therefore equivalence classes generated by 1 and 4 are going to be same. Similarly, if we take order pair 4, 7, then their difference is also -3. It is divisible by 3. Therefore, equivalence classes of 4 and 7 are also same. So you can see the pattern here. If I add 3 to 1, I obtain 4. Then 4 plus 3 is 7. 7 plus 3 is 10, and so on. So all these equivalence classes are going to be same. And now I can see, or I can observe that if I consider 2, and if I add 3 to 2, I will obtain 5, and order pair 2, 5 is in given relation because 2 is related to 5, because 2 minus 5 is -3 divisible by 3. Similarly, I will have 5 plus 3, 8, 8 plus 3, 11, and so on. So now you can see I have all the integers here: 0, 1, 2, 3, 4, 5, 6, 7, 0 and positive integers. Now we can talk about negative integers also. Suppose I consider -3, 0, then -3 minus 0 is divisible by 3. Therefore, equivalence class generated by -3 is also in this category. Similarly, this will continue. Here I can write -6. Same thing here. If I subtract 3 from 1, I will obtain -2. So we know that -2, 1 belongs to R, because -2 minus 1, that is -3 divisible by 3. Therefore, equivalence class generated by -1 and 1 are equal. Similarly, equivalence classes generated by -4 and -1, -4, -1, -3, that is -4 and -1. This is also an element of R, because -4 plus 1 is -3 and it is divisible by 3. So here I can see that for if I consider negative integers, then also equivalence classes are same. -4 minus 3 will give me -7, and -7 minus 4 belongs to R, because -7 minus -4, that is -3, is divisible by 3. So now you may have the idea that we will have only three distinct equivalence classes, and equivalence classes generated by remaining integers will be equal to equivalence classes generated by those three integers. So what we can do, we can find out equivalence classes generated by 0, 1, 2 or 3, 4, 5 or 6, 7, 8, and we can write that all the equivalence classes are equal to equivalence classes generated by 0, 1 or 2. So with this in mind, now we are first trying to write down the equivalence class generated by 0. So now we are using the definition of equivalence class. Equivalence class of 0 equal to all those integers y belongs to z such that 0 is related to y, or we can write that order pair 0y belongs to R. This I can rewrite as order pair 0y belongs to R. Now order pair is a member of R if the difference of components is divisible by 3. So here I should write that 0 minus y, that is minus y, is divisible by 3. And if some integer is divisible by 3, we can write it as a multiple of 3. Therefore I can write minus y equal to k into 3 or 3 into k for some integer k. Or this I can rewrite as I am interested in the values of y. So I can write from this expression, I find that y equal to minus 3 times k. K belongs to z. Now this k is any integer, so we can consider different values of k, and we can write down some elements of this set. Here it is obvious that y is nothing but multiple of 3. If I take k equal to 0, I will obtain 0. If I take k equal to 1, I will obtain minus 3. For k equal to minus 1, I will have 3. For k equal to minus 2, I will have 6. And here also I can continue. For k equal to 2, I will have minus 6. For k equal to 3, I will have minus 9. And here also we can continue with 9 also. If I take k equal to minus 3, I will have 9 here, and so on. This will be infinite set. This is the equivalence class generated by 0. And we know that these integers are nothing but relatives of 0. All these integers are related to 0, and we know that if two elements are related to each other, equivalence classes generated by those two elements are always same. Therefore, I can see that equivalence classes generated by all these members which are in this equivalence class will be same. Equivalence classes generated by 3, 6, 9 up to so on, and minus 3, minus 6, minus 9 up to so on are all equal to this equivalence class. So in this way we can find out equivalence class generated by 1 and 2 also. Suppose we consider equivalence class generated by 1, then I have to write all those integers which are related to 1. So I directly write ordered pair 1 y belongs to R. Now y belongs to Z. So ordered pair 1 y belongs to R if difference 1 minus y is divisible by 3. So we can write it directly as a multiple of 3. K belongs to Z. And I am interested in the value of y. So this I can rewrite as, from this, if I take y on right hand side, I obtain y equal to 1 minus 3k. K belongs to Z. And for different values of k, we will have different integers in this equivalence class of 1. For example, if I take k equal to 0, I will have 1 here. If I take k equal to 1, I will have 1 minus 3, that is minus 2. If I take k equal to 2, I will have 1 minus 3 into 2, that is 1 minus 6, which is minus 5. If I take k equal to minus 1, I will have 1 plus 3, that is 4. If I take k equal to minus 2, I will have 1 plus 6, that is 7. And here there are infinite number of elements. Here also we can write, we can take k equal to say 2, then we will have 1 minus 6, that is minus 5. If I take k equal to 3, I will have 1 minus 9, that is minus 8. So you can see the pattern here. Difference of any two elements, successive elements, is 3 or minus 3. If I consider 7 minus 4, I obtain 3. If I consider 4 minus 1, I obtain 3. If I take 1 minus minus 2, I obtain 3. Or if I am considering difference in this way, 1 minus 4 is minus 3, 4 minus 7 is minus 3, and so on. That means elements are in such a way that difference of any two elements is a multiple of 3. And these are the elements in the equivalence class generated by integer 1. And as we have discussed, equivalence class generated by all these integers will also be equal to equivalence class generated by 1. And in a similar way, we can write down the equivalence class generated by 2 also. Equivalence class generated by 2 equal to all those integers y such that they are related to 2, that is ordered pair 2y belongs to R. Now ordered pair 2y belongs to R if difference 2 minus y is divisible by 3, that is 2 minus y is a multiple of 3, so I can write 2 minus y equal to 3 times k belongs to z, and this is equal to y belongs to z such that y equal to 2 minus 3k, k belongs to z, and for different values of k we will have different elements here. For k equal to 0 I will have 2, if I take k equal to 1 I will have minus 1, if I take k equal to 2 I will have 2 minus 6, that is minus 4, and this will continue in this direction. If I take k equal to minus 1 I will have 2 plus 3, that is 5. If I take k equal to minus 2 I will have 2 plus 6, that is 8, and so on. And this is the equivalence class generated by 2. And equivalence classes generated by remaining elements will be equal to equivalence classes generated by 0, 1 and 2. And here we have to mention that thing also in the answer. I have to write that equivalence class generated by 0 is equal to equivalence class generated by 3, then 6, then 9 and so on, and I have to continue for negative integers also, minus 3, then minus 6 and minus 9 and so on, or I can write plus or minus 3 plus or minus 6 in that way. Similarly, equivalence class generated by 1 and equivalence class generated by 4, 7 are same. So here I have to write equivalence class generated by 1 equal to equivalence class generated by 4, 7. I can write in this way, 4 plus 3, 7 plus 3, 10 and so on. If we are going on this direction we are adding 3. If we are going in this direction we will subtract 3. So if I subtract 3 from 1 I will have minus 2, then minus 2 minus 3, minus 5, minus 5 minus 3, minus 8 and so on. And equivalence class generated by 2 is equal to 2 plus 3 is 5, 5 plus 3 is 8, 8 plus 3 is 11, and in this direction 2 minus 3 is minus 1, minus 1 minus 3 is minus 4, minus 4 minus 3 is minus 7 and so on. So this is the answer. We have obtained equivalence classes for 0, 1 and 2, and for remaining integers equivalence classes are equal to equivalence classes generated by 0, 1 or 2. And now this is the final answer. Here we have to just write down the equivalence classes generated by the elements of set of integers. But we can observe few things here. If we take the union of all these three equivalence classes generated by 0 is, let me write again, it is 0, 3, 6, 9 and so on. Here minus 3, then minus 6, minus 9 and so on. Equivalence class generated by 1 is nothing but I have to start with 1 and I have to add 3 on right hand side and subtract 3 from left side. So 1 minus 3 minus 2 minus 3 minus 5 minus 3 minus 8 and so on. Equivalence class generated by 2. So I have to start with 2. 2 plus 3, 5 plus 3, 8. and so on. 2 minus 3 minus 1 minus 1 minus 3, that is minus 4 minus 7, and so on. Now if I consider intersection of any two equivalence classes which I have written here, then you can see if I take intersection of these two sets, no element is common. Here we have multiples of 3 and there is no multiple of 3 here. So we can say that these two equivalence classes are disjoint. Similarly, if I consider intersection of equivalence classes of 0 and 2, then also you can observe that they are disjoint, and equivalence classes generated by 1 and 2 are also not having any element in common. And all these equivalence classes are subsets of set of integers, and if we take their union, you can see if I take the union, then here you can see I have 0, then 1, 2, again 3, 4, 5, 6, 7, 8, 9, and so on. And in the negative direction, 0, then minus 1, minus 2, minus 3, minus 4, minus 5, minus 6, minus 7, minus 8, minus 9. So you can observe that if we take union of these three sets, we will obtain this set of integers. So here all these equivalence classes are subsets of Z. They are mutually disjoint. If we take intersection of any two sets out of these three sets, then we obtain empty set. Therefore we can say that this set of equivalence classes generated by this 0, 1 and 2, this collection is a partition of the set of integers, is a partition of Z, because union of all these sets is equal to set of integers and they are mutually disjoint. And we have discussed in last session also that if we have R as an equivalence relation on a given set X, then the set of equivalence classes of elements of X always gives us the partition of this set X. Here our set X is the set of integers and we obtain this partition of the set of integers. And this collection of equivalence classes is also known as quotient set of given set X by the relation R, and it is denoted by this notation X quotient R. So here we have quotient of Z by the congruence relation, or we can write in this way also. We are considering congruence modulo 3. Set of all equivalence classes generated by an equivalence relation is called quotient set of X by R. It is denoted by this symbol. So this is just for understanding. Our answer completes here. You have to just write down the equivalence classes generated by the elements of Z. So this is very important question. I hope I am able to explain it. If you have any doubts, you can ask in comment section. Thanks for watching.